Now we'll use by using closed loop method. For closed loop method, what we have to do is we have to make this P only controller. First step is we have to put this in closed loop. First step is we have to put this in closed loop. We put already in closed loop, and we don't want any I mode. That's why multiplied by 0. We don't want any derivative mode. Multiplied by 0. That also multiplied by 0. Only derivative mode. Only proportional only mode. Let us give gain smaller value. We will gradually increase smaller value. So let us give initially 1. Or let us multiply this by 50% of this value we will give. 2.22 multiplied by 0.25. 0.25. Let us start from here. 0.25. Let us give 2 initially and multiplied by 0.25. Apply. Small gain I gave. I am seeing the response. Steady state error is there. Where it is settled 0.35 only. What is the set point? 1, but it is settled at 0.35. If I increase the gain, what happens to the response you see? If I increase the gain, this is the advantage of simulation. If you do all this simulation, we can understand many things. If I make gain more, if I increase the gain, 2 multiplied by 0.25, how much? 0.5. Am I correct or not? Now I am making this 0.5. 2 multiplied by 0.5, how much? 1. I am giving 1. Now what is the response? What is the response? You see? Now, where it is settled? Earlier it is settled at 0.35. If we increase gain, it is settled at 0.5. But still steady state error is there. It is not yet settled at 1. If I increase the gain to further, 1.5 times. So I am increasing the gain 1.5 times 2. 1.5 times. 0.5 times now. 1.5 times. 1.5 times means what? How much? 2 multiplied 1.5, how much? 3. No? Okay. Now you see the response. Proportional only controller. Definitely steady state error will be there. Where it is settled? Settled at 0.7. Steady state error is decreasing. As gain increases, steady state error decreasing, but more oscillation. More oscillation. Steady state error decreases. That is the only advantage. Now let us starts oscillating, means gradually increase the gain, starts oscillating, For 0.25, no oscillation. 0.5, slight oscillation. Now 3, gain is increased from 0.25 means 0.5, 1, 3. Now let us give 5. What happens? Let us give 5. Let us multiply it by 3. 6 I am giving. Deliberately I am giving 6 and check the response. Unstable. It becomes unstable. So it must be less than 6. K max must be less than 6. I know the value of K max. That's why deliberately I skipped that value. If I give multiplied by 2, multiplied by 2, 4. Now how much gain I gave? 4. See the response. Sustained oscillation. By using Routh criterion, you can find the value. For that fourth order process, if you find a Routh criterion, K max equal to 4, you will get. So sustained oscillation, you got for K max. For K max, you got the sustained oscillation. Now we have to find the TU. So for that, enlarge this and find K TU. TU equal to how much? Where it matches the scale. Here almost it matches the scale. Almost here it matches the scale. Here 45. Here it is 39. 6 almost. 6, you know. TU equal to 6. 6 or 5? 6. 6. So here, there you can amplify and see. Here also you can amplify and how to amplify. Here you can amplify this and see. This you have to double. You can amplify and see like this. Time axis has to be amplified. If you amplify and you can see more coordinates so that you can find correct value. I know 6, I know. That's why I'm telling that 6. So you can see here, and it is 6. That's why now we know these two values. That's why we can find the tuning parameters now. What is tuning parameters for these two values? We got K max equal to, we got K max equal to 4 and TU equal to 6, we got 6 seconds. From this, we can find the tuning parameters. For KC, it is 0.5 times K max. Therefore, KC equal to, for P only controller, for P only controller, for PI controller, for PID controller, KC is 2.5 times. No TI, no TD. TI, TD. For PI controller, it is 0.45 times. 0.45 times means 1.8. 1.8. This is TU by 1.2. 6 divided by 1.2. How much? How much? 5. So, no TD. For PID controller, how much you are getting? This is here 0.4, it's 0.6 times 2.4 you will get. What you will get? TU by 2 means here you will get 3. Here TU by 8, how much? 0.75. That's all. Now we'll see. This is the best tuning parameter using Ziegler-Nichols. Why? There, from the reaction curve, we approximated TD, we approximated TP. This is not exact value. But here, by simulation, we got the exact sustained oscillation. That's why by Ziegler-Nichols method, it must be 1.2. But reaction curve method, how much you got? 2.2 you got. Here you got 2. Here you got 2.2. Here, what is that? 2.22 multiplied by 0.9 is 2. But here, what you got? 1.8 only. Nearest value only you are getting in reaction curve method. There is no wrong in it. That's why it is retunable. If you get more oscillation, you can reduce gain. You can increase TI. You can reduce TD. Like that, you can do adjustments. It is not a fixed rule. That you can modify after seeing the response. This is only thumb rule. So now let us do simulation for all these parameters. 2, 1.85, 2.43 and 0.75. Before that, what is integral of error? Integral of E dt means you are finding error, absolute error. So error like this means you are making the graph like this and finding integral. That is absolute error. Integral of square error means integral of e square dt means you are squaring this value. If you divided by 1.35 multiplied by 1.2. How much? 2.2. 2.67. Okay. Here 2.67 divided by 2.67 divided by TI equal to how much? 1.35 multiplied by 3.33 multiplied by 3.33. Yes, I got. Here 2.67 multiplied by TD equal to how much? Not 33 for this divided by what is that? 8, you know. Divided by 2. Okay. Here TD KC multiplied by TD. TD equal to how much? Multiplied by 0.5. 0.0675. Okay. 0.675. 675. Okay. These are the tuning parameters for PID controller. Now let us run. Which gives better response? Reaction curve is better because gain is more. Reaction curve is better because gain is more. If you increase slightly Kc, response become better, but at the cost of oscillation. Another thing is threat to stability. Threat to stability. We are going close to j omega axis. That's why threat to stability. These are the two reasons, but response will be better. These are all up to us to find tuning parameters. One will be better anyhow. If Kc is more, because here Kc is higher value, 2.6, here only 2.2. That's why reaction curve gives better response than sustained oscillation method, but at the cost of more oscillations and threat to stability. That's all. So with that, but you have to do for P and PI in the lab, but I did only for PID.